Dear students, welcome to another lecture on structural analysis. We are going to continue with analysis of continuous beams and portal frames using moment distribution method. So in this example, what we are having is we are again having a portal frame, and A is hinged and D is fixed. The loadings that we are having. Dear students, welcome to another lecture on structural analysis. In this lecture, we will be continuing with our discussion on moment distribution method for the analysis of continuous beams and portal frames. So in this question, we are having a portal frame, end A is hinged and end D is fixed. The loading is as shown in figure, and we have columns which are 6 meter in height and beam which is 4 meter in height, and also the moment of inertia of all the sections are the same. Now the very first step in the analysis is we need to calculate the fixed end moments. And do you know how to calculate the fixed end moments? And we have calculated the values of fixed end moments for as MAB equals minus 75, MBA equals plus 75. Similarly, MFCB has been calculated as minus 50 and plus 50 respectively. Same is the case with MFCD and MFDC. Accordingly, has been calculated as minus 75 and plus 75 kilonewton meter. Now, having calculated the fixed end moments, the next step is to calculate the uh, distribution factors. So how do we calculate the distribution factor? The table has to be made. The first column will be of joints and the next column will be of members. Then you have the relative stiffness, which is I by 6, I by 6, I by 4, I by 4 and I by 6, I by 6. Then we can calculate the distribution factor using the formula K divided by sigma K. So if we substitute, we will get the values as 1, 0.4, 0.6, 0.6, 0.4 and 0 respectively. That is for a hinged end. 1 because it is a end hinge, and 0 because it is a fixed end. Okay, and the other values has been calculated accordingly. So having calculated this, the next step is we need to do the moment distribution. So we have to go to the moment distribution table. So this is the moment distribution table. The first we will be having the joint, then we will have the members. So in the member, at A we have only one member, that is AB. At B we have two members, BA and BC. At C we have two members, CB and CD, and at D we have only one member, that is DC. Next column is of distribution factors. So distribution factor, we have it is end hinge, so the distribution factor is 1, and BA is the distribution factor is 0.4. Here it is 0.6. Here again it is 0.6 and it is 0.4 here, and the value of distribution factor to fixed end is 0. Now having calculated these values, the next row we have to add is the row for fixed end moment. So AB was minus 75, this was plus 75, it was minus 50 here, this is plus 50, this is minus 75, and this is plus 75. Now the next column is to balance it. Okay, so which are the supports that has to be balanced? The end hinge as well as the interior supports. Let us start with the end hinge. So end hinge means the moment is 0, so we will add a plus 75 here to balance and make it 0. So once end hinge is completed, what we will do is, let us say we have to close this. Okay, so we will never add any of the values in this particular column. So let us simply strike down that particular column so that we will not be entering any values there again. Okay, next is we need to equilibrate the interior supports. So we have plus 75 here and minus 50 here. So the net unbalanced moment is 75 minus 50, which is plus 25. So we need to add minus 25 to B so that B will be in equilibrium. So if you add minus 25, that minus 25 has to be distributed among BA and BC in the ratio of their distribution factors. So we will have minus 10 coming here, which is minus 25 into 0.4, and we will have minus 15 coming here, which is minus 25 into 0.6. In a similar fashion, the unbalanced moment here is 50 minus 75, which is minus 25. So to balance it, we need to add a plus 25, which will be distributed in the ratio plus 25 into 0.6, which is plus 15, and plus 25 into 0.4, which is plus 10. So this will be the nature of distribution. Next step is we need to carry over. So we will never carry over to the end hinge or the overhanging end. We will only be carrying over to all other supports. So we will not have any carryover to this side. It will not be, for example, this carryover will not be there. So from here we will carry over, so that will be minus 7.5. Here we will carry over, it is going to be plus 7.5, and this would be plus 5. Okay, now what the carryover will do is the carryover will disturb the equilibrium of the interior supports, so we need to balance them again. So we are going for another balancing. This is cycle number 1, so the next balancing will take it to cycle number 2. Okay, so 7.5 has to be balanced. We need to add minus 7.5, which will be distributed in the ratio minus 7.5 into zero point 0.4. So minus 7.5 into zero point 0.4 will be the distribution. Also, before we do that, the look, one thing we have to remember here is uh, where do we carry over? Okay, we have to carry over to all supports except the overhanging or the end hinge. Okay, so if you look in this particular row, if you look in this particular row, the only point where there should not be any carryover is this particular point. This is the only point where there should be not be any carryover. Now we have carried over to this point, we have carried over here, we have carried over here. Now the however, we have not carried over at this particular point. Okay, there has nothing been carried over. So we have missed it out in the previous step. So what we have to do is this 75 has to be carried over to here. So what we are going to get is we are going to get plus 37.5 here. Okay, so that completes the carryover step. Once again, where do we carry over? We have to carry over the balancing moment. What are we carrying over? We are carrying over the balancing moments. Okay, so the balancing moment, okay, has to be carried over to all supports. It is not really supports, to all beam ends except at end hinge, or it is overhanging moment. Okay, so except in these cases we have to carry over again. Now if you look in this particular case, we need to find out where we missed out. For example, the mistake that we made is we did not fill 2 points. So one place that we, in this particular carryover row, if we look, one place that we did not fill is so one place that we did not fill is this particular point. So why we did not fill this, but why we did not fill here? Because we will never carry over to an end hinge. So that is the reason why we are not filling anything here. This moment is not carried over to here because there is no carrying over to the end hinge. So that carrying over is not there. Now next point we have to fill is this particular point. So is it we do we have to carry over here? Of course we have to carry over. So we will carry over half of 37, half of 75, that is 37.5 will be carried over here. Now next point is we will be carrying over each of the forces. Now when it comes to here, we have a plus 10 here which will be carrying over to plus 5. Okay, so this carryover is also done, and there is no moment here that we can carry over to this particular point. So that is not the only vacant point, will be this one. Now what carryover has done is it has disturbed the equilibrium, and we need to again find the balancing moments so that equilibrium is done. So 37.5 we have to add to 7.5, which to get the net unbalanced force. So to get the net unbalanced force, now to get the net unbalanced force, what will we do? We need to calculate the total unbalanced force, and to which we have to add the values. So what we are going to get is, we are going to get 37.5 plus 7.5, it is 45. We need to add minus 45, and is distributed in the fashion minus 45 into zero point 0.4. We will get it as minus 18, and here we will get minus 27. Minus 7.5 can be balanced as, we have to add plus 7.5. Again we have to distribute it, we will get 4.3, and we will be getting 3 here. Okay, so that completes the second cycle of balancing. Next again we have to carry over. Okay, we have to carry over again. So again, how do we carry over? Let us start from the first point. We don't have to carry over here because it is an end hinge. Next place we have to carry over is this particular point, but since there is no moment here, we cannot carry over anything here. There is no balancing moment at this point, therefore we don't have to carry over anything here. Next point is this. Okay, so here we will be carrying over half of 4.3, which will be 2 point, this is 4.5, half of 4.5, which will be 2.25, and here we will be carrying over minus 13.5, and to this end we will be carrying over plus 1.5. So this is the how we do the carryover. Now once the carryover is done, it disturbs the equilibrium of the interior joints, so we have to balance again, which takes us to balancing 3. So basically what we have done is we have done around 5 cycles of balancing, and after having done the 5 cycles of balancing, the if you look, the balancing moments are very small, less than 1 kilonewton meter, and where we will stop the further cycles of balancing and moment distribution. Now all we have to do is we have to add all the values in each of the columns. So if we add the values, we will get them as, this is 81.93, this is minus 81.93, and this value is 55.71, this is minus 55.71, and here it is 85.4. So this is how we calculate the n moments. Okay, so once the n moments are calculated, we can draw the bending moment diagram. So this is how we are going to draw the bending moment diagram at this is A, this is B, C, and D. So at A the bending moment is 0, at B the bending moment is 81, so we mark an 81 here. Okay, so this is 81.9, and this is also 81.9, and the bending moment at this point is 55.7, this is also 55.7, and the bending moment at this point is 85.4. So we can join them by straight lines, which gives us the support bending moment diagram. Okay, and the simply supported bending moment diagram will be triangles. We can simply superimpose them. The magnitude here is 150 WL by 4, this is 100, and the magnitude here is also 150. So this will be plus, minus, negative, plus, negative, negative, this will be plus, and this will be minus. We can mark the highlighted areas represents the active bending moment diagram. So this is how we draw the bending moment diagram for a portal frame. Okay, now the same problem can be seen as a continuous beam. So if you want to see the same problem as a continuous beam, all you have to do is express them in this fashion. Okay, so if we express it in this fashion, this is 6 meter, this is also 6 meter, and this is 4 meter. So A, B, C, and D, the loading are all central, and each has a magnitude 100 kilonewton. Okay, now the solution, method of solution, the moment distribution table, answer, everything will be the same for this. The only difference is we have, this is a beam and the other one is a portal frame. Now how do we draw the bending moment diagram? So we have 81 here, we have a 55 here, and we have an 85 here. Okay, so this is 85, this is 89, and this is 55, and then you superimpose it with the simply supported bending moment diagrams. So this is 150, this is 100, this is 150. So plus, minus, plus, minus, plus, minus. Okay, so this region represents the bending moment diagram for the continuous beam having the same loading. Okay, so what you can do is, once you know the analysis of a continuous beam, you can do the analysis of the portal frame, or if you know the analysis of the portal frame, you can do the analysis of the continuous beam. The basic moment distribution remains the same in both the cases. Okay, so hope you have understood it. Now what we will do is we will discuss one more problem, a slight variation of the same. Now here the problem that we are going to consider is the loading, everything is almost the same. Okay, However, here what we are having is we are having the portal frame is having a slight overhang. Okay, so a slight overhang is there. Now what do we do in these kind of cases? In this kind of cases again, like we did for beam with overhang, we have to transform it to a fashion like this. Okay, we have to transform it. So whatever the effect of the overhang has to be transformed as a 25 kilonewton acting on the column plus a clockwise moment of 50 kilonewton meter. That is, a positive moment of 50 kilonewton meter is going to act at C. So this step is very important. To do the moment distribution, this transformation of the overhanging portion to the equivalent moments and force is very important. The force is not going to affect the moment distribution. However, for clarity of understanding, we will be representing the force also as the effect of this particular overhang involves that force also, but it is not going to affect the analysis of the moment distribution. However, the shear force diagram, that is going to have impact. Now let us try to see how we will do the moment distribution. The table almost remains the same. We will not be doing the calculations. We will only try to see what difference it is going to make. So if we look into the moment distribution table, how do we draw it? First we should have the joint. So joints are A, B, C and D. So these are the four joints. Then we need to draw the members. Members will be AB, then it will be BA, BC, CB, CD and DC. So these are the members. Now next thing is we need to mark the distribution factors. So members, next is distribution factors. So the distribution factor for the hinge end is 1. The rest was 0.4, 0.6, 0.6, 0.4 and here it was 0. Now the distribution factor is also over. Next we had the fixed end moments. So it was minus 75. This is plus 75, this is minus 50, this was plus 50 and this was minus 75 and this was 75. Okay, now next stage is the balancing stage. Now in the balancing stage we need to be very careful here. First thing is we need to see, let us try to see what should be the moment that is occurring at each of the interior support. If we know A is a end hinge, therefore the moment there should be 0. Okay, the moment there should be 0. Now B is an interior support and interior support should be subjected to equilibrium. So we do not have any special consideration, but the only consideration is it has to be in equilibrium. Now when it comes to C, if we know that the C is having a concentrated moment that is acting at the point, the effect of the overhang is a concentrated moment acting at a C, and that concentrated moment is a moment of clockwise 50 kilonewton meter, that is a plus 50 kilonewton meter is the net moment that is acting at the point C. Now D is a fixed end, so we don't have to do anything. Now what we have to understand is when we equilibrate the joint B, the net equilibrium, we have to reach a net moment as 0, whereas when we try to balance joint C, we need to ensure that the moment here is 50 kilonewton meter always. Okay, so what we will do is let us start the balancing stage. To balance the end hinge, we have to apply a plus 75 here. Okay, so once that plus 75 is done, we should no more do any carryover here because that joint has already satisfied its uh, conditions. Okay, its bending moment condition has already been satisfied. Now when we go to joint E, joint E is having a net unbalanced moment of 75 minus 50, that is 25. So if we try to redistribute it, we are going to get minus 25 into 0.4, that is minus 10 here, and we are going to get minus 15 here. When we come to joint C, we are having 50 minus 25 minus 75, so the net unbalanced moment is minus 25, and what we require is we require a net moment of plus 50 acting at the joint C. So what we will do is we will add a plus 75 here, and when we add this plus 75, that plus 75 has to be distributed among the members uh, in the ratio as shown. So how do we redistribute this plus 75 in the said ratio? So if we try to add plus 75, plus 75 into zero point 0.6 is plus 45, and plus 75 into zero point 4 is plus 30. Okay, so if you now try to calculate the net moment here, you will see that it is plus 50, which is satisfying this condition. So once this condition is again satisfied, we will no more be dealing with the joint C. Joint C is already done. We will no more touch joint C again. Okay, there should not be any carryover to joint C, because joint C has already completed its uh, distribution. Okay, so and this is a fixed end, you don't have to balance the fixed end. So having done this, now next stage is carryover. So where all will we carry over? We will be carrying over to all the points other than points um, where we have close where the or moment condition has been arrived. For example, at A moment condition has been arrived, at C also the moment condition has been arrived. We will not be carrying over to these ends, the rest we will be carrying over. So let us start from the first balancing moment, 75. 75 has to be carried over to this point, so that will be 37.5. Now minus 10 has to be carried over to A, but A is an end hinge and the moment condition has been reached, so we will not carry over. Minus 15, minus 15 has to be carried over to here, but since we have already the moment condition has been reached at C, we will not carry over. Next is minus 45, so that has to be carried over here, so it will be 22.5. Next we have 30, that 30 has to be carried over here, so it is going to be 15, and we have no moment here to carry over. So what carryover has done is it has disturbed the equilibrium. So once the equilibrium has been disturbed, what we need to do is we need to further do the analysis. So if we try to balance it, what we are having is we are having 37.5 plus 22.5, that is 37.5 plus 22.5 is 60. So 60 has to be redistributed, so we need to add has to be balanced, so we need to have minus 60. So minus 60, if we try to add, it is going to be minus 24 here, and we will be having minus 36 here. Okay, similarly if you look here, we don't have to touch this portion, and here also we don't have to do anything. So if you look here, uh, now all the beams have all the interior supports, all the fixed supports, all the end support, everything has been balanced. Okay, if we try to do any more carryover, let us try to do a carryover. Okay, if we try to do a carryover, what is going to occur is we can okay, if we try to do a carryover, this cannot, the possibility is carrying over to this side, the only two balancing moment are these two, and we can carry it over to here. However, carrying over is not permitted here because it has already satisfied its moment condition. Similarly, the other balancing moment is this. If we try to carry over to here, since it has already satisfied its moment condition, we do not have to carry over there also. So this, by the second balancing act itself, the beam has reached its final stage. So now what we have to do is, instead of going for the carryover, we have to stop our analysis and let us try to find the final moments. Okay, so if we try to find the final moments, the final moment here is 0. If we try to add this, we have 75 minus 10 plus 37.5 minus 36. So we have 66.5 coming here. the moment on the other side has to be minus 66.5. So this value is minus 66.5. The moment here is plus 95 and the moment here is minus 45 and the moment here is plus 90. Okay, so these are the final moments. Now if we look here, usually we are having a continuity of the moments. For example, MBA, this is AB, this is BA, this is BC, this is CB, CD and DC. Usually MBA will be equal to minus MBC. Okay, and however, if you look here, MCB is not equal to minus MCD. Well, the reason is that we are having a concentrated moment there. So whenever there is a concentrated moment, there is going to be a jump in the moment values at that particular junction. So we might have seen the same in shear force. Whenever there is a concentrated force coming, the shear force diagram will have a sudden rise or a fall. Similarly, whenever you have a concentrated moment, the bending moment will have a sudden change. So if you try to draw the bending moment diagram for this case, the bending moment diagram will be, so if we try to draw the bending moment diagram, we have a 0 here and it is 66.5 here, 66.5, and then it is, so it is 66.5 and let us say this is 66.5. It increased to 95 and here it is only 45 and at this point it increases to 90. So if we try to draw the diagram would be something like this. So this is 66.5, 66.5, 95, this is 45 and this is 90. We can superimpose. This is 150, this is also 150 and this is 100 from the previous example. So this is positive, negative, negative, positive, negative, negative, positive, negative. Okay, so this is our active bending moment diagram. So if we try to draw the same for a beam, this is 6 meter, 4 meter, 6 meter, and we have central loads 100, 100, 100. So if we are having a 50 kilonewton meter load at C, now if we try to do the analysis for this particular beam, we are going to get the same result and the same moment distribution table as we got in the previous case. The bending moment diagram will be, we will have a 0 here, it will be 66 here, it is going to be 95 here, then you will have a sudden drop there and then it will again rise to 90 here. So it is 0 here, 66.5, 95, 45, 90. Is 150 here, this is 100, this is 150, positive, negative, positive, negative, positive, negative. So once again if we try to color it, So this would be our active bending moment diagram. Okay, and if you see the bending moment diagram at the point C, you can see that there is a sudden fall in the bending moment diagram. So that indicates that there is a concentrated moment acting at that particular point. So with this, we complete our discussion on bending moment diagram, and I mean analyzing continuous beams and portal frames using moment distribution method. So in the next lecture, what we will be doing is we will try to see conditions related to settlement of supports for continuous beams as well as sway for portal frames. Okay.